Okay, mechanical advantage. Let's suppose that you need to take a 100 kilogram mass and haul it up a height of 4 meters. Tough job. So we've got a mass of 100 kilograms. We've got an mg, the weight, 980 newtons. The work is force times distance, 980 newtons times 4 meters, 3,920 joules. Okay, so that's a pain. So you get a friend to help you. What's going to happen now? Your buddy here grabs a rope on the other side, and you both pull. Now, it's going to go up, say, steadily at a constant velocity, right? So there's no acceleration, which means the sum of the forces is 0. The weight equals the pull of both of the ropes. In other words, you only have to pull half as hard. I mean, that was the whole point of having your friend help. You pull half, and he pulls half. You both have to pull 4 meters of rope, but you're each doing half the work, so that load, 3,920 joules of effort required, is split between the two of you. All right, so what if your friend bails on you and says, I can't help, but I'll tie this here to the wall. And you're like, gee, thanks. Because what's going to happen now? You're going to try to pull the thing up. And this rope is going to go slack while you hoist up the box with the other one. So let's say it moves up 1 meter while you're pulling. You still had to do all the weight lifting. You had to do 980 newtons times 1 meter. You did 980 joules of work just pulling it up like that. And that other rope was just useless once you got started. Well, let's change the scenario some more. Suppose your friend still isn't showing up. They tied the rope there and left, but you made it one long rope, and you ran it over a pulley. All right, so what's happening now? Well, if you're just holding it still, you only have to hold half the weight because the other rope is holding the other half. It's not completely useless. It was the same thing over here if you were lifting it up a certain extent, except that rope was slack. So you had to lift all the weight there. Here you only have to lift half the weight because it's all one rope and it's taut on both sides. Both sides are pulling up. Right? Just as if your friend was there and you're both standing there holding it, you each would be holding half the weight. So you've got half the weight. You pull 4 meters of rope, you've done half the work. Did you just cheat conservation of energy? Did you get the thing out? No, you didn't, and here's the problem. You pulled up 4 meters of rope, but it only went up 2 meters. That's where you have to pay the piper. Because this rope got 2 meters shorter, and this rope got 2 meters shorter, you had to do the work of pulling 4 meters of rope, but you only had to pull 490 newtons of force. So you did half the work, and it got halfway up. So energy still conserved. All right. This is a mechanical advantage of 2, because you only need to do half the force. You're going to have to do it for twice the distance. I mean, you still have to do all the work, but it makes it more possible to do it. Mechanical advantage is multiplying your strength, multiplying your force by being willing to deal with it for a greater distance. That's the key idea of mechanical advantage. We're trading a force and distance back and forth. Now suppose you decide to use 2 pulleys. You've got one mounted to something really sturdy in the ceiling so it can take the weight. And you've got rope tied here, down to it, up, over, and you pull. How hard do you have to pull now? Does this pulley give us any additional mechanical advantage? It turns out no. It's just convenient redirecting so you can lean into it and use your own weight to help. But there's no mechanical advantage there. The reason is this mass is hanging by 2 ropes, right? So the weight is split evenly between the 2 ropes. You still have to pull with half the weight. You have to pull with 490 newtons. This is just redirecting things, but it's not actually giving any amplification. If you pull 4 meters of rope, this gets 2 meters shorter, this gets 2 meters shorter, and this doesn't change its length. You're not moving up and down. You're not moving closer to the pulley. So that pulley isn't doing you any extra amount of good. You still have a mechanical advantage of 2. What if we hook up the ropes a little differently? Let's take this case where we have 2 pulleys, and rework the rope so that it's arranged like this. So what's different? Since the end of the rope is tied to the mass, that rope is now going to be getting shorter. This gets shorter, this gets shorter. We have a mechanical advantage of 3. You have to pull 6 meters of rope for it to go up 2 meters, because this has to get shorter, this has to get shorter, and this has to get shorter. 3 ropes, 1/3 of the weight, about 330 newtons. The exact way the ropes are connected can matter, because in this arrangement, this distance wasn't changing. You only had 2 distances changing. You only had 2 ropes supporting the weight. So you had a mechanical advantage of 2. Each rope had half the weight, and you had to move twice as far. In this arrangement, you've got 3 ropes that are getting shorter, and so you get a mechanical advantage of 3. Now let's look at this situation. 3 pulleys. What's our mechanical advantage? How many ropes are holding the weight up? 1, 2, 3, 4 ropes are coming off of it. And so the weight is being divided by 4. So you only need to pull with half of 490, 245 newtons. The way you pay the price is when you pull 4 meters of rope, this thing only goes up 1 meter, because you have to make this rope shorter, and this one shorter, and this one shorter, and this one shorter. So again, trading force for distance. 1/4 as much force, 4 times the distance. If you want to hoist this up 4 meters, you're going to have to pull 16 meters of rope, because you still have to do all the work. So that's a mechanical advantage of 4. That's the basic idea of mechanical advantage.